Okay, in science we make a lot of measurements, and we record them in a very particular way. Scientific measurements are reported so that every digit is certain except the last digit. The last digit is always an estimated digit. So here we have two different tables comparing carbon monoxide concentrations in parts per million recorded in Long Beach, California in these different years. Over here, we've got 6.9, 6.1, 4.1, 2.5, 1.9. Here, the concentration is recorded to the nearest tenth of a part per million. Here, the concentration is recorded to the nearest 1 part per million. Now, a scientist looking at these numbers understands that the last digit is estimated. So what that means is for 6.9, we would assume that it's estimated to the plus or minus 1 in that last digit. So looking at 6.9, this tells me 6.9 plus or minus 0.1, so that's 6.8 to 7.0. It's in that range. There's uncertainty. Measurements cannot be exact. It's just not possible. Over here, if we're recording it as 7, 6.9 would round up to 7, right? But here, there being only one digit, there must be uncertainty in that digit, and so I understand that to be between 6 and 8 parts per million. A much broader estimation, right? Not as accurate. Scientific measurements are always recorded with all the digits that we're sure of and one estimated or uncertain digit. And this is a skill we're going to need to use in lab. So how many digits get recorded depends on what we use to measure the thing, okay? So a thing to remember is read between the lines. That means we look at whatever lines are on the device and we're going to estimate or read between the lines. So here the example, we're measuring the mass of a pistachio on this little kitchen scale. Now there's ounces and grams. We're going to choose grams because we're in chemistry class. So we look at this scale and we kind of orient ourselves. Here's 0 and this one's 10. So that's 10 grams. And there are 10 divisions in between. So each of those small red lines represents 1 gram, right? So we see that the moving mark here that tells us the mass of the pistachio is between 1 and 2 grams. Can you see that? Is there any uncertainty in that? No, it's between those lines, right? It's more than 1 gram and less than 2 grams. No doubts about that. So we record 1 point something grams. Because the 1 is what we're certain of, and we're going to estimate the next decimal place. These divisions in grams are 1 gram, so we're going to estimate tenths of grams. So we look at this black line and we say, well, I think that's about 2/10 of the way from the 1 to the 2, and so I'm going to record this as 1.2 grams. Now the person next to me might say, no, I think that's 1.3 grams. That's fine. It's an estimate. We don't all have to come up with exactly the same number, but we will all agree on the 1 gram. Anybody have any questions? So the principle here is that you estimate 1 decimal place past the smallest division. So if you're using a ruler and the smallest divisions are 0.1 centimeters, that's typical on a ruler, we're going to estimate to 0.01 centimeters. On a thermometer, the glass thermometers we have, the smallest divisions are 1 degree Celsius. We estimate the next decimal place, so 0.1 degrees Celsius. Read between the lines. Let's practice. So here's a thermometer, and that's in degrees Celsius. So we're going to look at it and say, well, what are those smallest black lines representing? 1 degree, right? This is 90 degrees, and you go 1, 2, 3, 4, 5, 6, 7, 8, 9, and there's 100. So we're going to estimate to the next decimal place to 0.1. So we find the red, it's actually alcohol, and it's a little, they didn't do this picture very well, it's kind of hiding here behind the 100. But we see where that lines up over here, and it should be pretty clear that it's at a little above the 8, right? So that would be 100, no, that's not 8, my bad, 3, right? The third line. It's right in, it's right in there. So 103 point something. And this is where you give it your best shot. You say, well, maybe I think that's 103.1 degrees Celsius. Any questions? Here we have a 10 milliliter graduated cylinder, and we're measuring the volume of water. You notice how the water curves like this? It almost looks like there's a contact lens or a bowl or something sitting on top of the water. That's called the meniscus. We'll learn later that that's caused by surface tension, but water does that. So we have to know which part of the water are we measuring. Devices such as graduated cylinders are calibrated so that you measure the bottom of the meniscus. So the very bottom of this surface here. And we look at this graduated cylinder, and this is 4 milliliters, and that's 5 milliliters. So the divisions represent 0.1 milliliters. That means we estimate the next place. So we find the meniscus here. This is 4, so it's 4 point something. So this is 4.5, and it's less than 4.6. We got 4.5. Those are the digits we're certain of. We're estimating, reading between the lines to see what the next place is. What do you think? 8? 7? Okay? What I'm going to be looking for when you make measurements in lab, I can't really check everybody and see, did you write it down right? Did you measure it correctly? But I can tell, did you use the right number of decimal places? So if you're making a measurement in this graduated cylinder, I'm going to look for 2 decimal places, and if you only have 1, or if you go crazy and have 3 or 4, I may take points off, okay? If you're not certain if you're recording it correctly, ask me and I'll help you. I'd like everybody to be clear on this very soon, okay? Questions? So that brings us to significant figures, which we've kind of been hinting about. So the precision of a measurement depends on the precision of the instrument. When we do calculations with measurements, funny things can happen. We've already seen some calculations with the calculator where it gives us all these garbage numbers, right? It just keeps going and going and going. So we need to do something with the results of our calculations so that we don't misrepresent the precision of the measurements. So we do this using significant figures. It's not a perfect method of keeping track of error and precision, but it's a lot easier than differential calculus, right? So we'll just do with the Sig Figs. So what do we call a significant figure? They're also sometimes called significant digits. These are the non-place-holding digits. These are all of the certain digits and the one estimated digit. Anything after that is meaningless, okay? The greater the number of significant figures, the greater the certainty or the precision of the measurement. So more significant figures is good. So we need to learn what to identify as a significant figure. The issue is zeros, okay? So here's the rules from the textbook. Non-zero digits are always significant. So if it isn't a 0, you count it as a Sig Fig. People don't have trouble with that. It's the zeros. There's actually 3 kinds of zeros. There are zeros that are interior. I also think of them as trapped zeros. So here's examples. In the bold, that's a trapped or an interior 0. That's not a placeholder. That's in the middle. It's trapped in the middle. Here's some other ones. Those are inside. They're not just holding a place. Those are considered significant figures. Then we have zeros that come at the beginning of a number. They're called leading zeros. So this number, 0.00023, those digits are just holding a decimal place. They don't actually reflect measurement. Let's think about it. Well, what if we measured something that was 2.5 centimeters? Could we put a bunch of zeros in front of the 2? We could. It looks dumb. Do I know that that place is 0? Sure I do. But we don't write numbers like this. Here, those are zeros in the beginning, but they're there because we have to hold the decimal place. If I leave those out and say 0.23, it's going to be very confusing. Leading zeros go away when we put the number in scientific notation. To put this into scientific notation, I'm going to put the decimal point after the first non-zero digit, so 2.3, and then I have to figure out how many places did I move the decimal point. Well, it was here, and I moved it 1, 2, 3, 4 places, so times 10 to the 4. The tricky thing is, should it be a positive 4 or a negative 4? The right-left thing, positive, negative, that doesn't work for me. This is how I do it. I look at this number and I say, that's a small number. How do I feel about small paychecks? I feel negative about small paychecks. This is a small number, so it has a negative exponent. When we write the number in scientific notation, all those tricky zeros go away because the times 10 to the negative 4 holds the decimal place for us. Zeros that come at the beginning of the number are never counted as significant figures. Trailing zeros. So the explanation I'm giving here is slightly different than what's given in the textbook because this is what makes sense to me. It will get you the same result, so use whatever method works. So trailing zeros, we're going to count them as sig figs if there's a decimal point physically written in the number. So here, 39.0. Do we need the 0 there to hold a decimal place? No, if we took that 0 off, it would still be 39, right? We're writing that 0 because it's measured. It happens to be the estimated digit here, but the decimal point tells us we count that 0. Here's 120.00. There's a written decimal point. All of those zeros are going to be considered significant. And over here are 2 more examples. So look and see, is there a written decimal point? Then you count trailing zeros. Trailing zeros before an implied decimal point are ambiguous. We can't tell what the writer meant. Are those significant? Are they not? So what we're going to do is we're going to try to avoid them, but we're still going to run into them. We're going to assume the worst case scenario. We're going to assume that they are not significant figures. So those kinds of zeros are illustrated here. The number 300. Well, is the 3 the estimated digit? Is the first 0 the estimated digit? Is the second 0 the estimated digit? It's not clear. So we're going to assume that those zeros are not significant. So 300 without a decimal point says between 200 and 400 to me. That's a very general estimated number, right? If we want the second 0 to be the estimated digit, we can write it as 300 with a decimal point. That would be to the nearest 1. So that would be 299 to 301. So you can stick the decimal point there. That's still not the best way to do it. The best way when you have trailing zeros is to use scientific notation. So if we put that in scientific notation, this one we would write as 3 times 10 to the 2. Because 300 is a large number. And how do I feel about large paychecks? I feel very positive. So it's a positive exponent. So that one I would write as 3 times 10 to the 2, indicating there's only one significant figure. This number where I added the decimal point in scientific notation, the decimal point indicates that those zeros are significant. And so then I'm going to write that when I put it into scientific notation. This is going to take some practice, and that's part of what the worksheet today is about. So this number here, 100,000, is there a decimal point written in the number? No. So should we count those zeros? No. How many sig figs does that number have? 1. That's not very many. So there's measurements, and then we have exact numbers. We can consider an exact number to have an unlimited or an infinite number of significant figures. So 3 kinds of exact numbers. Exact counting of discrete objects. How many fingers am I holding up? 3. Is there any uncertainty in that? No, it's exactly 3. They can be counted. So there's no sig figs there. It's exact, and so if you have to say how many sig figs, you say, well, it's infinite number of sig figs. Another type of exact number is an integral number that's part of an equation. Integral meaning an integer. So the diameter of a circle is 2 times the radius. This is an integer that's part of an equation. It's exact. The diameter is exactly 2 times the radius. So I would not consider the 2 when I was counting sig figs. The other type is defined quantities. So 1 foot is exactly 12 inches. It's defined that way, right? 1 foot equals 12 inches. I guess I should write the example here. 3 fingers. So defined quantities come up a lot in conversion factors. Some conversion factors are defined, some are not. If you are within the same measuring system, so within the English system, like this, feet and inches, that is defined, that's exact. If you are within the metric system, and you're saying, well, 10 to the 3rd meters is 1 kilometer. That's defined. That's exact. Going between the English system and the metric system, many of those, in fact, most of those are not defined. They have a finite number of significant figures. The one exception I want you to remember is that 1 inch is exactly equal to 2.54 centimeters. They actually slightly redefined the inch so that it is exactly 2.54 centimeters. Okay. Let's practice. Identify the number of sig figs in these measurements. So 554 kilometers. How many sig figs? 3. That one should be relatively easy because there's no zeros in it. 1.01 times 10 to the 5th meters, 3. So in scientific notation, all the digits in this first part of the number are significant, and these are all placeholders. So scientific notation makes things easier. 1.4500 kilometers, 5. Trailing zeros with a written decimal point, we're going to count those. So that's 5. 7 pennies. Well, it's got 1 digit, but that's an exact number because we can exactly count 7 pennies. So the question says, how many sig figs? Infinite. It's not 1. There's 1 digit in the number, but I could say this is 7.00000000. I could go on for the rest of the day writing zeros, and it would be true. Exactly 7. Okay, so infinite. 0.00099 seconds. 2. This is like playing some weird game, right? So these zeros at the beginning, leading zeros, are not significant because they're holding the decimal place. When we put that number into scientific notation, it becomes 9.9 times 10 to the something. Right? It'll be 10 to the 1, 2, 3, 4, minus 4. Those zeros go away because they get wrapped up in this times 10 to the something. That's the place holding part. So that one has 2 sig figs. 21,000 meters. I would, if you're pressed for a number, I'd say call it 2. It's ambiguous. So on a worksheet or something, I would accept either answer, 2 or ambiguous.
So if it was on a test, we can either put 2, like both answers?
Yeah, this sort of a question on an exam would be multiple choice.
Oh.
And I don't set out to trick you for the most part. So I would not put 2 and ambiguous and expect you to choose between those. I'd put like 2 and 5 and infinite, and there would be one correct answer. Any other questions? Okay, so we've learned to count sig figs. Now we need to learn what to do with them when we do calculations. The result of the calculation needs to reflect the precision of the quantities that were used in the calculation. We shouldn't gain or lose precision just by doing math on the numbers. So we have rules for calculations. There are 2 types of calculations. Multiplication and division are related to each other. Addition and subtraction are related to each other. They're kind of opposites of each other. So there's a different rule for each of these. We'll look at multiplication division first. So in these operations, the result has the same number of sig figs as the factor with the fewest significant figures. So we're going to look at the numbers that we're using. Here all the math is done for us. 1.052 times 12.504 times 0.53 equals, this is what the calculator gives us. What we're going to do is we're going to look at the first number and say, okay, well that one has 4 significant figures. The second number has 5 significant figures. This third number has 2 significant figures. The 0 in front of the decimal point is not a significant figure. And then this is the easy part. Which is smaller, 4, 5, or 2? Well, 2 is the smallest. So that says I need to round this number to 2 significant figures. So I'm going to keep the 6 and the 7. We'll talk about rounding in a minute. I'm going to keep the 6 and the 7, and I look at the next digit. The first one I'm going to get rid of, it's a 2. And so I round down to 6.7. What I would encourage you to do is to always write at least 2 extra sig figs in your result and then round it and show all of that on your paper. Here's an example of division. The math is done out here for us. Again, we're going to look at how many sig figs in this number, how many sig figs in that number. And so this one has 3, that one has 5. We're looking for the one with the fewest sig figs. And that's how many sig figs we're going to round our answer to. So we're going to round to 3 sig figs, 0.626. That leading 0 doesn't count. And so then we express the answer as 0.626. Any questions? Adding and subtracting, different rule, okay? Here we're looking at decimal places, not the number of significant figures. So the result will carry the same number of decimal places as the quantity with the fewest decimal places. So the rules here are very similar. One's counting sig figs, the other's counting decimal places. So it can be helpful to stack the numbers up like you were going to add them by hand without a calculator. I would encourage you to just go ahead and use the calculator because your brain does weird things sometimes, and this isn't math class where we want you to use your brain to do simple math. Go ahead and use a calculator. If you want to keep your brain sharp, do it the hard way and then check your work. So adding these numbers together, this is what the calculator says. The rule says fewest number of decimal places. So this number has 3 decimal places. This has 2 decimal places, and this one has 4 decimal places. Right? So the smallest one is 2. 2 decimal places. We round the answer to 2 decimal places, 5.41. So that's the rule. Let's look at it a little more detailed to try to understand why it is that way. So, assuming that these are measurements, what is the uncertain digit in 2.345? It's the last significant figure, right? So the 5 is the uncertain digit. I'm going to underline that. In 0.07, what's the estimated digit? The 7, right? And in the last one, the 5. So those digits were estimated. We're not certain about those. In our result, we want to keep all of the certain digits and just the first one that's not certain. So when we're doing the adding here, we're adding 5 to blank spaces. Math says, well, assume that's 0, but I'm not sure about the 5. That was an estimate. So when I add 5 to empty spaces, is this 5 a certain digit or an estimated digit? It's estimated. So I'm going to underline that one. The next column over here, oops, didn't mean to do that. I've got a 5 that's estimated, a blank space, I don't know anything about that one, and a 7 that's certain. When I add those together and get 12, is the 2 certain or uncertain? It's uncertain, because that 5 might be a 6, or it could be a 4, we don't know. So this 2 is uncertain. In this next column, I've got a 4 that I'm certain about. I'm certain about the 9, but I'm uncertain about the 7. That makes the result uncertain. So this 1 is uncertain. The next row, I've got a 3 that I'm certain about. This 0 is not considered a sig fig, but it's certainly a 0. And then a 9 that I'm certain about. When I add those together, I am certain of the 4. So everything to the left of this is going to be certain digits. So what I want to keep is I want to keep all the ones that aren't underlined and the first one that is. So that's 5.41. Any questions? Here's another example with subtracting. So this line here, what are we doing with that? Well, we're stacking up these numbers, lining up the decimal point like they taught you in elementary school, and making sure that all of our digits are lined up in columns. And then we're going to see which number stops first. Well, this one stops first. I'm going to draw a vertical line, and that's going to tell me where my answer should end. Here, this 0.07 was the number that stopped first. It had the fewest decimal places. So I drew the vertical line, and then the answer is the stuff before the vertical line. So here, 5.679. I'm going to keep the 5 and the 6. This number had 1 decimal place. This has 3. So I'm going to keep 1 decimal place. This 7 tells me that this number is closer to 5.7 than 5.6. So I'm going to write the answer as 5.7. Any questions? Okay, rounding. So you look at your certain digits, your first uncertain digit. You're going to look at the next digit, just the next one, not anything after that we don't even care about. The next digit, the first one that we're dropping, we look at that. If it's 4 or less, in other words, if it's under 5, you round down. If it's 5 or greater, we round up. Very, very important that we do not change the magnitude of the number when we're rounding. Okay? This is where people just do things that later they say, oh wow, that was really stupid. So let's do an example here. Let's say I have this number and I want to round to 3 significant figures. What is the name of that place? So this is the ones, remember? Tens, hundreds, right? Here it says, be very careful when rounding to the tens place or higher. In such cases, it's wise to put the number into scientific notation before rounding. Because the common thing that I see happening is people say, okay, I'm rounding to this place. The 7 tells me I round up, and they say, this is 125. You can't round 12,478 and get 125. What's missing? Some placeholder zeros. Okay, so if you don't want to use scientific notation, we're rounding here. Okay, that's fine, but then all of these places before we get to the implied decimal point have to be replaced with zeros. It's a lot safer to do it in scientific notation. So I'm going to put this into scientific notation. 1.2478 times 10 to the, and implied decimal is after the 8, so I'm moving it 1, 2, 3, 4 places. 10 to the 4th. That's a big number. I feel positive about big paychecks, so it's a positive exponent. Now I look at that third significant figure, and I round it, and I say, well, that's 1.25 times 10 to the 4. I didn't change the value of the number. Any questions? Watch out for that. It happens every semester, multiple times. Examples of rounding, if we are to round each of these numbers to 2 significant figures. So 5.37, I'm rounding to the second sig fig, the 3. I look at the 7, tells me to round up, that's 5.4. 5.34, keep the 5 and the 3, I look at the 4, that tells me I round down, so it's just 5.3. 5.35, okay, that one's right in between, but the rule says round up, so that's 5.4. 5.349, I'm keeping the 3, I'm looking at the next digit. I am not going to look at the 9. Sometimes students want to start at the end and round everything backwards. That's a lot of work, and it sometimes gets you the wrong answer. Don't look at those, just look at the 4. 4 is less than 5, it's 5.3. Okay? Multi-step calculations. This happens a lot. What we want to do is we don't want to round each individual step. We want to keep some extra digits, and we want to do our rounding at the very, very end. Because when you round individual steps, you can introduce error into your measurements, and that's not something we want to do. So here's an example. We've got 5.78 times 5.903 times the quantity 5.489 minus 5.01. So we're going to look at the subtraction here. When we do the subtraction, it gives us 0.479. That's what the calculator shows us. We need to think about, well, where would the last significant figure be? Where's the uncertain digit there? Well, the rule for adding and subtracting is fewest decimal places. This has 3 decimal places, that has 2 decimal places. The result would have 2 decimal places. I'm not going to round it yet, but I want to indicate to myself where the number ends, where the sig figs end. So I'm going to underline the last significant figure. I'm going to keep that 9 along for the ride. And then I've got my other numbers here, and I'm going to do the math. Now I've got all the same type of operation, multiplying. So I multiply those, I write down what the calculator says, and then I look at rules for multiplying. Fewest number of sig figs. So here I've got 3 and 4 and only 2. The 9 is written in there, but the line tells me that only the 4 and the 7 places are significant. So 2 sig figs, so then I'm going to round this to 2 significant figures. I'm going to keep the 1 and the 9. I look at the next digit, it's a 1. I round down. My answer is 19. Any questions? Let's do some more examples. So here we've got a whole bunch of numbers. This is all multiplication, okay? So do all the multiplication, write down the answer. So let's do that. 3.10007 times 9.441 times 0.0301. I'm sorry, there's division in there too, but division uses the same rules. So I'm doing that math, and I'm writing down what the calculator says. That's a lot of digits. Anybody else get that number? This means yes. This means no. Anybody? Thank you. Okay, so multiplication division use the same rule. What's the rule? Fewest number of sig figs. So we're going to look at what we were multiplying and dividing. How many sig figs? 6, 4, 3, and 4. 3 is the smallest, 3 wins. So I want to keep 3 significant figures in my answer. The leading 0 doesn't count. So I've got 1, 2, 3. I'm going to keep this place. I'm going to look at the next digit, and that tells me whether to round up or down. This one rounds up, and so I'm going to express my answer as 0.381. Now, do you have to write down all the digits your calculator gives you? You don't have to. You need to write some extras down, though. And I would say the minimum is 2. So when I'm doing this problem, I can look ahead and think, okay, I need 3 sig figs in my answer. So I'm going to write down the first 3 digits, and then I'm going to write down at least 2 more. You don't even have to worry about rounding. Just write down 2 more, and you'll be good. That way, if I need to use this number in a future calculation, I don't want to use the rounded one. I want to use the unrounded one. I've got the digits there. Or if I realize that I rounded it incorrectly or to the wrong number of significant figures, I don't have to do the math over again. I just have to round it again differently. Let's look at the next one. 0.881 plus 132.1 minus 12.02. Adding and subtracting use the same rule. You can do this on your calculator without writing any intermediate values down. So 0.881 plus 132.1 minus 12.02. My calculator is giving me 120.961. Adding and subtracting usually don't give you a lot of garbage. It's multiplying and dividing. So adding and subtracting, the rule is fewest number of decimal places, right? So this one has 3 decimal places, 1 decimal place, 2 decimal places. So I need to round this to 1 decimal place. So I'm going to keep the 9. I look at the next digit, it tells me I have to round up. So the 9 rounds up to 10. So this ends up being 121. I need a decimal place though. I need to put a 0 in there. That 0 is important because that's the estimated digit. If I don't write 0.0, then the 1 becomes the estimated digit, and I've changed the certainty of the measurement. Questions? Letter C, we've got multiplying, dividing, and adding. And so now we need to think about order of operations and applying the rules only to the operations that they apply to. So I have to apply a different rule to the adding than I do to the multiplying and dividing. So what I'm going to do on my calculator is I'm going to do the adding first. 44.11 plus 1.223. I'm going to press equals, and I'm going to make a little note of it here to myself. 45.333 is what my calculator shows me. I'm going to use the rules for adding and say this has 2 decimal places, this one has 3 decimal places, so my answer should only have 2 decimal places. So I'm going to underline the second decimal place to remind myself that's the last significant figure. I'm going to leave the 3 there, the second one, but it's not a sig fig. I just want to avoid rounding errors. So now I can take and do the whole thing. 2.5110 times 21.2 divided by 45.333. And instead of writing down all the garbage, I'm going to anticipate multiplying and dividing with this number. We're looking at fewest number of Sig Figs, right? This one has 5, this one has 4, this one has 4, because we're only going to count up to the underline. So my answer should have 4 significant figures. So I'm going to look at my calculator, I'm going to write down the first 4 digits, 1.174. That's my 4th significant figure. And I'm going to write down 2 extras to be safe. And then I'm going to round that, and that'll be 1.174. I should have boxed this one too. Any questions? $12.01 times 0.3 plus 4.811. Adding and multiplying use different rules, and so we have to apply those rules separately. So I'm going to look at the product here, 12.01 times 0.3. When I do that math, I get 3.603. Applying Sig Fig rules to multiplication, I'm looking at fewest number of Sig Figs. How many Sig Figs would this answer have? Not 2. 1. So 0.3 leading zeros, you don't count them. This has 1 Sig Fig. So this would have 1 Sig Fig. I'm not going to round it yet, but that's where the uncertainty is. Now I'm adding 4.811. So I'll just go ahead and add that on my calculator. And the answer is 8.414. But in adding, I look at fewest number of decimal places. So when this number is rounded, how many decimal places? 0. It ends in the ones place, right? This one has 3. That's nice and everything, but there's uncertainty in the ones place. Another way to do this is stack them up. 4.811. As you go from left to right, looking at that number, find the column that has an uncertain digit first. I'm going left to right, and that first column has an uncertain digit, right? So I'm going to put a line to the right of that column. And then when I write in my answer down here, 8.414, it tells me I'm going to stop at the 8 because there's uncertainty in the 3. And so when I add that to 4, there's uncertainty in the result. So this number, I know it's disturbing to some people, that's just 8. Okay? Any questions? Accuracy and precision, it's important to understand the difference between these. Accuracy is how close is your result to the true value? How correct is it? Precision refers to multiple measurements. How close are they to each other? Ideally, we would be accurate and precise, but you can be one or the other. You could be both. You can be none. So consider these results. 3 students weighing a block of lead has a true mass of 10.00 grams. Here are their, they did 4 trials, they weighed it 4 times, they wrote down what they got, and they gave an average. Now it's a little tricky to just look at this table of numbers and identify what's going on. Oftentimes it's helpful to graph this. So here we've made bar graphs of the student's data. So here's student A. These are the 4 different measurements they made. The blue line is the true value. The red dashed line is the average of the student's results. So was this average close to the true mass? Not really. Average was 10.13. and it's really 10, so that's not so great. And then look at how much difference there is in the heights of those columns. There's a lot of difference, right? This is not accurate, it's inaccurate, and it's imprecise. Here's student B. So looking at the average, they got an average of 9.79 grams. Is that real close to 10? No, this is way off. Inaccurate. But look how close those measurements were to each other. The student is precise. He's very good at getting the wrong answer, right? Does it reproducibly. So that's not so good either. And then here's student C. So student C got an average of 10.01 grams. That's really close to 10.00. Because when we look at the true mass being 10.00 grams, what digit is estimated in that? The last one. There is uncertainty in the 0.00 place. So this student came up with 10.01. Where's the uncertainty there? It's in that second decimal place. If there's a difference in the uncertain digit, we say that's fine. We know that's uncertain. So this student nailed it, right? Very accurate. And look at how close the results are. Very precise too. So that's what we're always aiming for. That's the difference between accuracy and precision. So student A was inaccurate and imprecise. There are two kinds of error. Random error has an equal probability of being too high or too low. And there's going to be random error in every measurement. The good thing about random error is that if you take a bunch of measurements and average them, the random errors generally cancel out. Because some are high, some are low, so you average a bunch of numbers together, it goes away. Systematic error is one that's consistently high or low. So student B, let's go back and look at student B. Student B here, all of his results were lower than the true result. That's a systematic error. Here, these are above and below. That's random error. This is random error. They're high and low. This is systematic error. In systematic error, you've got something going on, like maybe your instrument isn't calibrated correctly, or you're using it incorrectly, or you're weighing something and you've got your thumb on the pan, right? You're doing something stupid.